My name is Chris Bettinger, and I'm a faculty member in the departments of Biomedical Engineering and Material Science and Engineering at Carnegie Mellon University. My group is really focused on novel materials and microstructures for use in medical devices. And so our broad vision is essentially designing techniques and materials and fabrication methods for better interfacing medical devices with the human body. Electronic devices that are implanted in the body, such as pacemakers and nerve stimulators, they provide a lot of value in terms of therapies and diagnostics, but one of the challenges is that they become infected and they're very expensive and they're often difficult to deploy. So they require surgeons and highly trained medical professionals to accurately interface those devices with the proper organ in the body. And so we have designed sort of a new strategy to obviate many of those challenges with implants. And so the primary goal here is to basically take, let's say, a medical implant and condense that down into a form factor that you can eat. The central idea is that edible electronics can sort of circumvent a lot of these problems with permanent implants. So with edible electronics, you can do many of the same things that you can perform with implants. So you can perform sensing functions, you can deliver drugs, you can even maybe stimulate tissue inside the gastrointestinal tract. So one of the first challenges is simply power. How would you power a device that you could then ingest? So batteries are an important part of everyday life. They power your cell phones, they power your computers. So basically, in addition to performance and battery lifetime and these kinds of figures of merit, an ingestible battery would also have to be biocompatible, right? It has to essentially be non-toxic and also maybe to some extent have the same kind of performance metrics as regular batteries. So to address this initial challenge, we looked to nature to design batteries. Nature has a lot of interesting materials with unique physical and chemical properties. And so we actually were inspired by squid ink. So these are essentially materials that the squid sort of injects into the ocean to disguise itself from potential predators. And this pigment that the squid ink uses is melanin. This is the same pigment that's in our eyes and in our hair and in our skin. And so we essentially discovered that we can take that same pigment that already exists in our body and through some electrochemical processing, create a battery material that can not only supply power to ingestible electronics, but it's also a material that already exists inside of our body. So some of the advantages of edible electronics are that these devices can be deployed without the need of a skilled healthcare practitioner, and they don't need to be sterilized. For example, maybe the lunch or the breakfast that you had this morning or this afternoon is made of materials that weren't necessarily FDA approved in some way, but you're still probably walking around just fine. Whereas if you take those same materials and you implant them, you may have a very different sort of immunological response. Ingestible devices have a lot more latitude in terms of the kinds of flexibility materials, and that allows us to innovate new battery materials, new sensing modalities, and new structures for edible electronics more broadly. In the unlikely event that that device gets lodged at some point in the GI tract, the materials that we use are also degradable. So in essence, that can be if it gets obstructed, then that material will break down on the order of, let's say, maybe weeks or months. And so this is a lot different than more synthetic materials, which might get stuck in the GI tract and they have to be surgically extracted. And so that's obviously painful, risky, and very costly procedures to do that. So our kind of biologically derived edible electronics can really overcome a lot of those sort of global challenges with this space.